Here we're going to look at the fundamental theorem of calculus. And before we get to that, I want to go back and review a little bit from the very beginning. We were looking at taking the derivatives at the very beginning of this course. And we said that the derivative would give us the slope. And we started looking at the slope of a secant line where we looked at the change in y over the change in x. And we said if we made the points closer and closer, we would end up with our tangent line. And we said the slope there would be dy dx, which would be the change in y divided by the change in our x. Well, now we want to show in relationship to our integration, this definite integration, this is going to be the inverse of our differentiation. Well, if we look here, we were calculating the area, and we looked at this in terms of our delta y and delta x, and we could think of this as the delta y here is the change in your y, the change in your x, and we are multiplying here delta y, delta x to find the area, where delta y we could think of as either the length, or we could think of this as the height of our rectangle, and delta x as the width. And when we multiply that, we certainly get the area of this rectangle. Even though we're looking for the area under the curve, we're getting an approximation. And we said before, we went through this whole limit definition of the integral. We said if we take the limit as n goes to infinity, then we know that our rectangles that we're drawing in here are getting really, really small. And if they get small enough, we can define the exact area under this curve. For example, if I was to draw a mark here, from the line down to the x-axis, we could think of this line as being a very tiny rectangle. And if we find the area of this rectangle, and if I draw another one right next to it here, extremely close, here's our other rectangle here in green, and that's an area for that rectangle. We really don't have any area that's not underneath the graph. We're not getting extra and we're not leaving anything out, because our rectangles are extremely small as our number of rectangles go to infinity. So what we're really focusing on is when we were finding derivatives, it looks like we were dividing here change in y over change in x. And now for the integration, we are going to be multiplying the change in y times the change of x. So just kind of a way to think of this as this inverse relationship. Just like multiplying and dividing are inverses, here our differentiation and integration are inverses of each other. So now let's look at this fundamental theorem here. And the definition here says that if a function is continuous on our closed interval from a to b, and notice here again, this capital F is representing our antiderivative of our function little f. So if we look at the integral of little f of x dx from a to b, we know how to integrate this. But now what it says, if we find the integral, which is big F, we're going to evaluate. Remember when we looked at the integration before, the indefinite integrals, when we integrated, we had to integrate and add on, we'd have a function plus our constant c. Well, now we're going to take that function and we want to evaluate it at b, which is our upper limit, minus our function evaluated at a, which is our lower limit. And by doing so, we can find the definite integral without going through that real long, lengthy limit process of taking limit as n goes to infinity with using the summation. So let's apply that to this example, and this is one of those similar examples we looked at before, going through the limit process. But if we go from the integral of x dx from 1 to 3, if we apply this theorem up here, remember, how do we integrate? We take our x, we increase the exponent by 1, so this is understood to be x to the first. So we're going to add 1, so that becomes x squared divided by 2, and then we have to evaluate this at the limits from 1 to 3. Okay, now keep in mind it's the upper limit, the f of b here. This is your upper limit minus the lower limit. So we're going to take the 3 and substitute that in for x. So we would have 3 squared over 2. And be careful, it's always that minus the lower limit. So plug 1 in, we would have 1 squared over 2. And by doing so, we would end up with 3 squared, we would have 9 halves minus 1 squared is 1, so that would be 1 over 2. 9 halves minus 1 halves would be 8 halves, which equals 4. And if you notice over here at the side, I've already worked it out. We looked at this before. Our line is y equals x. And if we think of this in terms of the area under the curve, we end up with a trapezoid. And we said 1/2 b1 b2 times the height. We end up with the answer of 4. So you can kind of see the power of this fundamental theorem of calculus. This makes this very easy to calculate, and we don't have to go through this whole long limit process. Now, the reason I made you go through the limit process before is I wanted you to understand what's happening instead of just showing you, in a sense, this kind of shortcut with the integration. Now, if you notice here, we did not have to worry about adding on c. Because if you think about this for a minute, if we integrated here and we got x squared over 2, and if we were to add on a plus c, let me kind of go back and emphasize this. If we integrated and got x squared over 2, and then we said, oh, we want to add on our constant c, we don't have to worry about this constant, because once we integrate and we plug in these values, if we plug into 3, we know that we're going to get 3 squared, we're going to get our 9 halves, and we'd have 9 halves plus c minus our 1/2 plus c when we plug the lower limit 1 in. And what's going to happen? We're going to end up with 9 halves plus c minus 1/2 minus c, because we have to distribute this negative, and our constant terms are going to cancel out. So when we're doing this definite integration with our upper and lower limits, we do not have to worry about adding on our c, because they're always going to cancel each other out. The only time we have to worry about adding on c is when we have our indefinite integration when there are no limits. All right, so let's look at one more example here of how we can use the fundamental theorem of calculus to evaluate this indefinite integral. We have x minus 1 over x squared going from -2 to -1. So the first step here I would recommend is to maybe let's rewrite the problem so that this is in a form that we can integrate. So we would have x minus, if we move the x squared to the top, we would have x to the -2 dx. And now this is a more manageable form. If we integrate x, once again, we're going to add 1 to the exponent and divide. So that's x squared over 2 minus, add 1 to this exponent, we get x to the, be careful, -1. Because it's a negative, we're going to add 1 to it. So it's -1 divided by -1. And you'll notice I like to put brackets around, and then we would indicate that we are going to evaluate this with our limits from -2 to 1. Sometimes, just as a notation, sometimes you'll see in textbooks they're going to draw just a line here and say -2 to -1. And on occasion, you may see me do this as well. This just says that we need to evaluate this at the lower limit -2 and the upper limit -1. But I think a lot of times I found that my students I just kind of put a bracket around the whole part, and then I put my limits -2 to -1. And this is where you want to keep in mind it's f of b minus f of a. So that means we're going to start with the upper limit. So we plug in our -1, and if I plug a -1 in, we're going to end up with -1 squared over 2 plus, now let me back up here for a second. Notice we have x to the negative 1. This is probably going to be easier if we make that exponent positive. And I'm going to do that so you don't make a mistake. And we can also simplify here. We have two negatives. Our negatives here and the negative 1, those two will become positive. And then x to the negative 1 we can move to the bottom, so we have 1 over x to the first power. Okay, and I think this will be easier so we have fewer negatives to deal with. So now let's plug in our limits. And if we do so, if we plug in a negative 1, we get negative 1 squared over 2 plus 1 over negative 1. Okay, so there's the f of b minus f of a, where we're going to plug in our negative 2. So that's negative 2 squared over 2 plus 1 over negative 2. And if we simplify the expression here, negative 1 squared, we get 1/2 minus 1. And we end up with 4 over 2 minus 1/2. So 1/2 minus 1 is a negative 1/2. Minus 4/2 minus 1/2 is 3/2. So now we're left with a negative 1/2 minus 3/2, which equals negative 2. And that's the answer to our integral. So hopefully by now you can kind of see the power of this indefinite integration using our fundamental theorem. And keep in mind, it's always here f of b minus f of a. So in our case here, that means we're plugging in f of negative 1 minus f of negative 2. So always think the upper minus the lower, so you're thinking the top limit minus the bottom limit.